Okay, so a very warm welcome and a good evening to General Theory of Relativity. Uh, go ahead. Before I go ahead with this presentation, I just want to show you two things. One is this one that tomorrow at same Indian Standard Time, 8 o'clock, I've got this gentleman who is a Presidency University, visiting faculty, and he will be basically coming and talking about astroparticle physics and high energy physics. He's very qualified, Dr. Debanjan Bose. Same on my channel at around this time. So those who wants to know anything about astrophysics or what are the career that you want to do, what are the things that you should take forward, you're all you can very well join and talk to him. It would be around oh, Alessandro. Yeah, I think Alessandro is from Peru. Alessandro is from Peru. Welcome, Alessandro Paulo. Very good evening. Warm welcome from India and all our participants around the world. I think you are joining from the farthest part of the world. I think it is around 10 hours difference. So, Alessandro, very warm welcome. He's already in my Instagram, so that's really wonderful. Okay, so you can ask him questions regarding this. Apart from that, this lady is coming up, and what happened? Just a second. Yeah, this lady is coming up on the 3rd of December. She is actually working directly at Fermilab. And you all know what is Fermilab. I think really don't have to tell. It's one of the, I mean to say, the premier particle physics laboratory in US. She is an accelerator director, and she would be talking on particle physics. So anyone wants to learn anything about particle physics, career in particle physics, quarks, hadrons, etc., you are all welcome. You can just ask her any question. Dr. Sudeshna Ganguly, I have been following her up for a long time. Finally, she gave an appointment. I told, ma'am, please come and talk, because there are a lot of people who would be interested for particle physics. She is actually from Calcutta. Then she went to US. Dr. Debanjan Bose, also from Calcutta, went to TIFR Mumbai. So anything regarding your particle physics or anything like that, you are all welcome. Dr. Ganguly is a very nice person. She's kind of, I would say, a teacher in particle physics, but she's working as a scientist in Fermilab on something which is called muon G2 experiment. Okay, which will help people to understand something regarding fundamentals. So this is actually my, I would say, agenda. So these two, okay. Another thing I have not confirmed, but just to tell you that possibly on the 17th of December, another person, Dr. Kapil, he is basically a PhD on quantum computing. Okay, I think you all know about what is quantum computing. He will be coming on my channel to talk about what is quantum computing, what kind of preparation is required, what kind of career is required, what kind of all those things about quantum computing. Okay, Monica, if you can just mute yourself, that would be great. I think there is a sound coming up. Yeah, thank you. Thank you very much. Okay. So these are the two announcements. Now, another thing is that, see, in this webinar, which I'm starting in a minute or so, I won't be able to give you each and every details about general relativity process with Einstein and other physicists. So if you want to attend any live class on physics, mathematics, this channel you can subscribe, Physics for Students. So Monday to Friday, I'm trying, but maybe sometimes I feel tired, etc. I am conducting live classes from 9 p.m. onwards. So welcome, Prashant. You do not have missed much, but a warm welcome to this. So if you want to attend to any classes, I don't have a schedule, to be very honest, but I will tell you on Monday I'm doing a little bit of complex analysis, real analysis, tensor calculus, etc. So you can very well attend to my free live classes. These are on my channel. This is my new channel. I am sorry, those, I mean to say, this is actually published long back, but I am unable to upload videos because videos take a lot of time doing, editing, animating. So what I am doing, this channel is exclusively for general relativity, nothing else. Okay, so if you want to know more about general relativity right from the beginning, absolutely point zero, I mean to say, from the grassroots level, then you can join this. 8:15 onwards also I am available. So from 8:15 to 8:45 I'm in this channel, and 9 o'clock onwards I am on to my next channel, Physics for Students. This is something which is typically only related to general relativity. It is already 1 minute past 8 o'clock. So let us start with the webinar right now. Okay, so first of all, what I would like to show you is that what is a system. Okay, any question you can let me know on this. See, why I'm trying to tell you what is a system, because first of all, there I want to show you exactly that general theory of relativity is a classical system. Now you will tell, sir, we all know that general relativity is a classical system, but what I am trying to tell is that what are the features of a classical system. Let us go a little bit deep and let us understand that, and let us from there finally understand that why general relativity is a classical system. Not only that, you will also come to know, say for example, Monica, she is already a teacher, or Priyanshu or Omar or Anirban, who was already into physics. You will come to know exactly the difference between a classical system and a quantum system. I mean to say, deep inside, what is that? So first of all, I would like to show you that, say for example, this is a kind of a system. For example, we want to track the trajectory of a rocket. Okay, a mechanical system. It can be a thermodynamical system. It can be an electromagnetic system, anything, quantum system. That means it's a kind of a collection of interaction of events, and which allows us to predict that, okay, so if the rocket is going in this direction, tomorrow it will go, or on the next 5 minutes onward, it will go into this trajectory. So this is what is basically called a system. Now you might say that, sir, what is not a system? Yes, that is also true. There are certain things which are not a system. For example, force, for example, gravitational constant, speed of light, reduced Planck's constant, symmetry, and what you call electromagnetic field. Now, this field word itself is very deep. I will not be going in this webinar today, because I am explaining that in my lectures in quantum field theory. What we need to understand very closely is that these constants, G, C, H bar, these are not interacting with any other particle. These are constants. Force, it is a constant. Gravitational constant is a constant. So it cannot be included in what is called a system. Okay, so any doubt till now? Are you all okay? You can just unmute and say me hello, yes, or put up a thumbs up. All clear, Omar, Priyanshu, and others who are watching
Yes,
this?
sir.
All
Yes, sir.
okay.
It is clear to me. Yeah.
Okay, fine. Okay, great. Anybody willing to join? No, no, fine. Okay. Now from here, what we go is that these people are actually the pioneers of system. Just go through that. You don't need to understand. So Sadi Carnot, he was basically the first person to introduce the concept of system. And he is basically in thermodynamics. Those who are learning thermodynamics, you know that is called a Carnot's system, Carnot's theorem. So he is a very famous person, made a lot of contribution in system. Then you see Norbert Wiener and Ashby, they included this concept of system in cybernetics. Then this Austrian biologist Ludwig Bertel Fanli, I'm sorry for the pronunciation, also introduces it. That means that the concept of system, I'm not talking of physics, mathematics, biology, whatever, the concept of system actually started with these people. Second, you see, this is very, very important. Now, in physics, we can divide system into three parts. Okay, one is called a classical system, which is very deterministic. That means if I throw a ball constantly, it will come over here. Again, throw it, come over here. So I exactly know where the ball will land and where the ball will come back. Relativistic system, that means special relativity or general relativity, is also a deterministic system. I will come to the deep meaning of deterministic system. Quantum mechanics or quantum physics is a probabilistic system. Probabilistic means I can only tell maybe the electron is here, or with a probability density I can say maybe the electron might be here, or there is a high chance to be here. Clear? So that is what is called a quantum system, which is very probabilistic in nature. Now you see, from here I will straight away go to something very fundamental. Now it shows that classical system, Newtonian mechanics, obviously, quantum, in the case of quantum system, etc., what we do is that we get a kind of a wave function like this, and from here we try to calculate that where the electron would be, but the basic idea of what a wave function can be. So that can be basically told of what is a system. Okay. Now I think when I'm moving the mouse, that is why it is creating a problem. Okay. Now the question, okay, let me go back to the previous one so that you can see this. So here you see there is a question mark that special and general theory of relativity is only relativistic system. I mean to say general relativity. I have underlined general relativity. So can I call general relativity as a relativistic system or something else? This is the question, which is a very deep question, and I'm going to answer that so that you can understand that general relativity is something else, which is not purely a kind of a relativistic system. It is not a relativistic system like this. It is something else. What is that something else? I'm just going to show you. Okay. So here you see, if you, the moment you cannot see, please tell me, because I cannot understand that whether you can see it or not. Is it visible now?
Yes, sir.
Okay, okay. So general relativity, I would say that it is basically a general theory of geometry, not general theory of relativity. That is why I put a cross onto this part, and I have told that no, this is actually what we call general theory of gravity. I'm so sorry, I will use the eraser to move this. Okay, so why is that? Now I am going to show you. Okay, now you see this very closely. Let me remove this with the eraser. Why it is not happening? Ah. So now you pay attention. All of you can see this, right? Okay. Now you see in the left hand side part, this special theory of relativity, what I have written: inertial frame of reference, speed and velocity, these are experimentally provable, and these are all frames of reference. Try to understand. If you cannot understand, please question me, because if this part is not clear, we cannot move on to the next part of our webinar. What I am trying to tell is that special theory of relativity is mostly speaking about speed, time, space, velocity, frames of reference, this moving in this frame of reference, that moving in that frame of reference, something like that. Okay. If I talk of general theory of relativity, all these things which you can see here, all these things, non-inertial frame of reference, gravity, all those things, these are actually related to this: surfaces and curvature. I think you agree to this point, right? Because these things, gravity, geometry of space-time, these things are more related to the surfaces and curvature, while special relativity is mostly dealing with simultaneity and relativity and speed and velocity and frames of reference. Are you getting my point? I will show you. Once we go ahead with the webinar, you will be able to understand. So from here, what do we see? We see that general relativity is actually speaking about lot of curvatures, lot of surfaces, bending, twisting, etc. But special relativity is speaking mostly about what is called speed, velocity, etc. Okay, okay, fine. Now you see these things. Don't need to understand all those terms. Soumya, are you enjoying? Young fellow from class 9. So you see here this space-time manifold, Ricci curvature tensor, Schwarzschild metric, Einstein field equation. If you take this, I think more or less overall, if you can understand, these all of them consist of geometry rather than mathematics. Will you agree to me? You see space-time manifold, it is related to geometry. Tensors, mostly related to geometry. Coordinate transformation from flat space to curved space deals with geometry. Ricci curvature deals with geometry. Metric tensor, etc. We will soon see these are all related to geometry. That means what I am trying to tell, the first mental, I would say, mental preparation that you should have while learning general relativity is that it is mostly about the geometry and the mathematics of geometry and geometric structure of space-time rather than just this one, rather than only inertial frame of reference, speed, velocity, etc. It deals primarily with the geometry of space-time. Is it clear to all of you? I mean to say, are you slowly getting the concept? It will be more clear, but I want to make you
Yes, sir.
understand the basic
Yeah, it is
Yes,
ideas.
sir.
clear. Yeah.
Monica clear?
Sir,
Rohit Arsha clear?
sir,
Okay, great.
Yes, sir.
Okay,
I have a
okay.
question,
Yes.
sir. Sir, I
Yes,
have a
tell me.
question.
Yeah, please tell me.
Sir, the what is the concept of fourth dimension? It is, I think, very
I will
difficult
explain
concept.
you later.
Fourth
No, fourth
dimension.
dimension is basically length, breadth, height, and time. All of them taken together is called the space-time curvature, and that is what is called the fourth dimension. Okay, I mean to
Sir,
say
but
dimension. Huh.
Sir, the time dimension fourth axis cannot be drawn on the three perpendicular
Absolutely,
axes x,
absolutely,
y, and z.
absolutely. It cannot be drawn, so it is something like x, y, z, and this is the time dimension. So this time dimension actually takes in one single this kind of a thing, which is called a space-time continuum. So we get length, breadth, height, and time all taken together. We will come to that. Don't worry. We will
Okay,
uh, we
okay.
will we will come to this part. Okay. Somebody wants to admit. Just a second. Yeah, admit. Yeah. Okay. Sahil Kumar. Right. Just a second. So this is the basic idea, that we are talking more about the geometry of space-time. Don't worry, these things will soon become clear once we move into that, but I'm just wanting to make you a preparation. Now you see here what I am trying to show you. The general theory of relativity, all the gravitational time dilation, gravitational waves, all these are non-linear in nature. What do we mean by non-linear? That means which is obviously not linear, which is not going in a straight line. But here you see, this is something which I call it as covariant in nature. Okay, I will come to this covariant. Actually, this comes from the concept of tensor, covariant tensor. But what I am trying to give you an idea is that, say for example, because of a sessional exam. Yes, Salman, you can leave. Yeah, absolutely. You have got an exam. All the best to you. So what I'm trying to tell, if the laws of nature are moving in this direction, say for example, whatever, it can be force, momentum, speed, accelerative velocity, whatever, covariant means that the laws of frame will be absolutely according to this. This is what is called covariant, COV. Okay. Contravariant means, for example, if the laws of nature are moving in this direction, the observation will be moving in this direction, or absolutely opposite. Contra means opposite. So when I say it is covariant in nature, when I say it is covariant in nature, I'm trying to mean that the whatever happens, whether the frame of reference are changed, moved, stretched, whatever it happens, the laws of the nature will be the same and the observation will be the same. This is what is called covariant in nature. I will come to that. So let us understand that these are not linear, obviously not linear. It is not moving in a straight line. To sometimes go up, sometimes go down, this, that, etc. Different types of frame. And it is covariant in nature. That means the laws of physics are inconsistent. It is not that something will go inconsistent. It will go in the same direction what we are doing. I will show you that. Now you see here is a big relativistic shift. Try to understand what I'm trying to tell. I'm trying to tell that all the effects of special relativity, what are the effects? Time dilation, length contraction, speed, all those things, whatever, they, when it gets generalized, obviously from special relativity we move to general relativity, right? When they get generalized, then there is a huge paradigm shift. It's a huge paradigm shift from relativity. The obviously in geometry, in general relativity, there is mathematics, but I am trying to tell you that the mathematics that we have in general relativity is more geometric in nature. Are you getting it? Uttam, they and others. I mean to say, I cannot talk to anybody. Those who I can see. So it is.
Yes,
Somebody
sir.
wants to join. Ayushi wants to join. Yeah. It is more geometric in nature. Just a second. I cannot admit. Hold on. What is happening? Yeah. This is again gone.
But
Yeah.
so this geometry is non-Euclidean geometry, right?
Absolutely. You're very right. Who is this? Rohit Asha. Yeah. I expected that kind of an intelligent question from you. This is a non-Euclidean geometry, obviously. But what I'm trying to tell is that just this Lorentz factor root over 1 minus v square c square length contraction, the type of mathematics that you are doing in special relativity is not the mathematics in general relativity. So for the teachers like Monica and Omar and Anirban, etc., when you are teaching general relativity to your students, see, most of the time what happens is that we start with the tensor, partial derivatives. Don't do that. My request to all of you would be, when you're teaching general relativity or even a special theory of relativity, try to make the students think, trying to make the students think what is the preparation in mind that they have. Don't throw them into mathematics. I, being a teacher, I'm just suggesting you, don't throw them, okay, you have to do this, do that. No, first tell them what is the mental shift that they would have. What is the preparation? A kind of a warm up before you go to the gym. Are you getting it, Monica and others, those who are teachers? So try to make them a kind of a mental preparation, what they are going to face and what is the mental shift that they would have. If they are prepared, then if there is a pain, oh, I've got a muscle pain, I've got a muscle pain, then it is fine. Right? Then it is fine. But without the preparation, it becomes a problem. Suddenly it is a shock. Oh, difficult mathematics. Okay, yeah, Rahat, you can just ask me your question. Rahat, you have a question because you raised your hand? Maybe. Yeah. Okay. So from here, what we see is this one. You see all these things on the left hand side, on this left hand side, these are all what are called special relativistic effects. I mean to see areas of special relativity. Okay. Length contraction, time dilation, speed of light, everything. All of these are special relativity. Now, what is happening is that all of these are getting changed to what is called general relativity. All of these are getting changed to what is called general relativity. You see this one? So this is actually having a parallel transport, then tensors. So this is a change, transition from the see, special relativity, any high school good mathematics people, I think Soumya one, they are done with class 10. He can also learn mathematics of special relativity, but not general relativity. As Rohitasha was telling, it is a non-Euclidean geometry. So trying to make you aware that this is less relativity and more about geometry. And that is why I always tell my students that please do learn differential geometry first. Don't go directly into general relativity. Yes, Uttam, your question.
Sir, for learning special relativity, what level of mathematics is required?
Nothing. If you're
What
not
class?
going into derivatives, I think class 10 or just class 10, 11, general mathematics. If you don't even want to go to calculus, that also you can do. Just basic arithmetic, that's all.
Sir,
I mean to say, if
I'm
you're
in
not,
class 8 actually. I'm in class 8. If
so
I want
class
to
8,
do the mathematics,
if you know the square root and then logarithm, etc., I think you can learn.
oh yeah, okay, then it's okay.
Absolutely. Yeah, yeah, yeah. I mean to say, if you don't want to go to that level of details, you can learn. So that is why I tell that general relativity is a geometric understanding, curvatures, more intuitive, and it contains a lot of exotic mathematics. Because what I am doing is that I'm shifting from this entire area, which is this parallel transport, all those things, right, into a geometry of space time. And that is what I was just telling to Anirban and Monica, those who are teachers, that the biggest mistake that you make is that you directly jump into the mathematics. Please don't do that. You need to learn geometry. Rohitasha was telling non-Euclidean geometry. Yes, don't jump directly into the mathematics. You should have an ability to visualize things, visualization abilities, and an intuitive mind. So that is why general relativity is very interesting. Why it is interesting? Because it contains lesser amount of mathematics but more of intuition, thinking. So you might say, sir, what contains mathematics? Quantum mechanics. Quantum mechanics is very mathematical in nature. You really don't have to close your eyes and visualize. But general relativity will require your visualization. So to the teachers like Omar and Junaid and others who are watching me, Monica, Anirban, my request to all of you would be, first make the students aware what is coming. First, make them aware about the presentation or what they should be mentally thinking. Then go into the mathematics. Things will become easier. Is it clear till now? This part of the webinar, all clear? Everything going fine? Okay. Okay. Now I want to make you understand that what is a classical system. No, don't think that Newton's laws of mechanics are classical system. This is something different. You see all these physicists on the left hand side, Newton, Isaac Newton, Faraday, Maxwell, Einstein, what they predicted is a classical system. What do you mean by classical system? It carries a rule, okay, it has a set of principles, okay, and it has got an underlying logic. Underlying logic means if this happens, that will also happen. So if I get up in the morning, I will go to my college. If I am in my college, I will do my classes in mathematics. Okay, so it can predict the future and how the set of events will behave. That means given the condition, I am sitting in this room, whatever is happening in next 10 minutes time, I can predict what is going to come. Now here you see, this is something very important. If I get a kind of a system like this one, okay, this is a system, this part. So I got a charge, I got a photon, etc. And I assume that it does not exchange with any matter. That means it is basically an undisturbed system. Okay. Now, if I take this kind of I would say this one, this is a coin. But the good part is that this coin has only got a head, nothing else. So if I say to Soumya, from head, where will we go? Soumya will obviously say, sir, from head, you can only go to head, head, and head, nothing else. Right? That means the future, try to understand, this is called the evolution of a system. The future of this system is what? Only head. That means mathematically we can tell the future will predict only the observables, that is only the head, nothing else. Is it clear? I got a coin which has got a head and the future is only head. Now here you see, if I move from head to tail, okay, classical system moves smooth. So if I tell what is the future of head, then you will say tail, from tail to head to tail to head, fine. And you see here we say that this is only a head, right? This is only a head. So from head, if I'm going back to head, just a second, why people wants to join so late? I don't understand. So from head, if I'm going back to head, then what I'm doing from head, again I'm going back to head, and from tail I'm going back to tail. This is very important. I will tell you why. This actually shows the predictiveness of a system. From head I am going back to head, and from tail I am going back to tail. And if this one, this particular part, you see, this is evolving with time. This is the clock. Okay. So what is it? Is called a dynamical system. So 1 minute, 2 minute, 3 minute, 4 minute, slowly the system will evolve. Slowly the system will evolve. Just hold on. Again, somebody wants to join. This becomes a problem. I'm doing something and hold on, my mouse is. Why people join so late? I don't know. Anyway, so it will evolve, and this is how it is called. So this is basically what is called a dynamical system. So we got a head, it will only show head, and whatever it happens, it will show accordingly. Now you see this one. Please pay attention. Say for example, this is which is called a reversible system. Now see, from this position, point number 1, I got an arrow which is going to point number 2. Say for example, I am here, and whom will I take? Let us take Soumya, my young boy. He is at point number 2. Okay. And from 2, Soumya again can go to point number 3. That means from point number 3, he can again come back to point number 2. Now, this is what is called a reversible system. That means if I know the state of the future, I can come back to the past. And if I know the past, I can again go back to the past, or I can know my present. Okay. So this is called a reversible deterministic system. Now, why I am showing you is that this system and quantum system is fundamentally different. And that is why you see general theory of relativity till now have not been able to find graviton, or we are not being able to find what is called a theory of everything. You will soon see yourself why it is so. Now pay attention to the figure below. What happens suddenly? Soumya, I hope you don't mind, I'm just taking your name because you are very young, just like my son, even younger to my son. Yeah. So this system, if I am at point number 2, okay, can I tell where I am earlier? No, because I am suddenly at point number 2. I am suddenly at point number 2, and this system is called an irreversible system. When I am at point number 2, that means from here I cannot know where I was, and I cannot know where I will go, because suddenly I am at this system at point number 2, and this is what is called an irreversible system. You tell me what is an irreversible system, I will come to that. In quantum mechanics happened. M. Khan, sir, your mouse pointer is not visible. Okay, yeah, okay. So this is what is called a reversible and an irreversible system. Now you see this. In physics, we have something which is called a spontaneous emission. Now, I will just be very simple with that. Sorry. Again, yeah. Spontaneous emission means something that, say, for example, there is a photon which is emitting an energy. I will show you the photograph, you will understand. And what is happening out here is that this amount of energy which is released is just a second, yeah, it releases what is called a quantized amount of energy. Quantized amount of energy means a certain amount of energy which is very quantized. Now you see what is happening out here in this kind of a system. And the left hand side you can see classical electromagnetism says that it is not quantized. It is not quantized in the sense, what it means is that classical mechanics always says that energy can come at any level. It can be infinite, it can be continuous. But what quantum physics says, no, it is only this much. It is only this much. That means it is quantized. So because it is not quantized, the electromagnetic field is not quantized, and that is why spontaneous emission is an irreversible process. Okay, now let me give you a quick example of spontaneous emission. For example, you know what are fireflies, neon lights. These are spontaneous. Suddenly it emits, and the electron cannot go back to its state. I will show you. Now, question is that, am I teaching quantum physics or I am teaching general relativity? No, I am teaching you general relativity, but there is a reason what I am trying to tell. Spontaneous emission is an irreversible process. What do I mean? Look here. This particular I would say electron, okay, this has emitted an energy, fine. So from this energy it goes back to E1 level, whatever, it has emitted a photon. For example, this electron has emitted a photon and it goes back to E1. Now spontaneous emission tells that from E1 it cannot go back to E2. So here I have written, once the spontaneous emission has taken place, it cannot go back to the original lower energy state. Why? Because the system does not return to its original state at the emission. This is called spontaneous emission. That means once the electron has emitted a subatomic particle, it won't be able to go back to that state. Now try to imagine here what is happening. Do you now understand? If this person is standing over here, he cannot go back to here. Clear? Are you all clear? I mean to say, you can say me yes or no. This person standing over here cannot go back here. That means it is a spontaneous emission. But this person can go from here to here, come back to here. Clear? Ayushi, hi, good evening. So is this portion clear to all of you? All 22 people? Okay, fine. Okay, now you see this diagram. Here is this is the what you call, this is the subatomic particle. Okay, now here it has actually emitted a, this is what Ayushi, can you tell me? This is gamma. This is the photon. Okay, now point number one, hear it out. If it has emitted a photon, this photon can go here. It can go to infinite amount of places. Now it is impossible that the photon can come back to the original state. Why? Because it has got infinite direction. Clear? Okay. Now say for example, this has emitted, and say for example, it can come back to this. If you use the mouse pointer, please, we can understand the page where you tell about. Mouse pointer, how will I use? I don't know. Okay, can you see this mouse pointer now? Here. Okay. So what I'm trying to tell is that now if it has already, say for example, it has come back, it is not guaranteed to return to the atom to its original excited state. Why? Because I have lost a lot of energy. I am running from my home to college and I have lost a lot of energy. So how do you expect that I will come back to my original state? Point number two. Point number three is that, for example, it has emitted and it has come back also to the original state. It tells that the reabsorb process is not instantaneous. That means the time that it has taken, let me show. For example, the photon is over here and it has emitted and it has gone back here. And the time elapsed, T1, is so that the photon in the meantime has interacted with many small particles, many small particles, and it has lost its energy and it cannot go back to the original E1 state. What I'm trying to tell you is that why a system or a state is irreversible and why it cannot go back to the original state. It has got infinity over here, it has got what you called it has lost its energy, and even if it goes back, then it won't be able to actually get into the state because it has interacted with matter and it has lost its energy. Any question till now? Anything you cannot understand? Yeah, Anirban, tell me.
Sir, infinity state is it state in quantum mechanics?
This is called renormalization. Infinite amount of possibility which the photon would emit. Are you getting my point? This is called renormalization. We really do not have, the mathematics shows so much of infinity that classical physics or even quantum mechanics cannot explain. So we need to take something called quantum field theory. Okay, I will just give you the essence. So here you see what I'm trying to tell, that this is Schrodinger's equation.
Sir,
Ayushi, if you can just mute yourself, that would be great. There's a lot of sound
sir, I have a
coming from.
question.
Yeah, Rohit, yeah, tell me.
Sir, if we like for an electron, like if in an atom, if we provide some energy to it, it goes to some another higher excited state. But then after
Absolutely.
some time, it goes back to its original state and emits some energy.
Right.
Then, sir,
No,
how it?
no, that is not in case of a spontaneous emission. You are trying to excite the electron with some external force.
Okay, that is controlled.
That is control, absolutely. Spontaneous emission means in nature what happens. For example, fireflies, they have moved their hand, it emits. So in that case, spontaneously it cannot go back. You are probing something, you are putting something so that it excites and then it goes back to the state. Okay.
Yes.
Right. So here you see that is why Schrodinger's
But
equation.
can we say like it occurs in a form of lasers also?
If laser
As
is a
in lasers.
spontaneous emission, yes, then it is,
Yes,
yes,
sir.
laser is actually a spontaneous emission. Very good point by Ayushi. Yes, it is a spontaneous emission. In that case, it cannot go back. Thank you very much. So here you see, this is actually why Schrodinger's equation in quantum physics, most of the people, they really don't understand the class. I have to tell again and again. So I just want to make you understand, is highly classical in nature. Please try to understand. Quantum mechanics, Schrodinger equation is definitely quantum in nature. But as itself, the left hand side and the right hand side is basically the kinetic energy and the potential energy. And that is why Schrodinger equation cannot explain spontaneous emission. Immediately Ayushi will ask me or Rohitasha will ask me, sir, what can present spontaneous emission? That is called the Dirac equation. I'm not going into that. Then again, I have to go into quantum physics. What is important is that the limitation of classical mechanics is that it cannot trace or cannot get to the mathematics where things are going back, or it is in a spontaneous state. If things are not going back, then it is a spontaneous emission, then I cannot explain things. So Schrodinger's equation is very much equal to F equals to ma. If you go back to my quantum field theory lectures, I have mathematically shown just by substituting the wave equation, we can get back the Schrodinger equation. Okay, we can get back.
I have a question.
Yeah, just a second. Just a
No,
second.
sir.
Yes, tell me.
Sir, I want to ask a question about Schrodinger equation. Sir, if we remove the iota in this equation, so what will happen, sir? Equation will not work. Schrodinger equation.
I need to check it. Means no, so, no. I will tell you. You can contact me later because this is something. Again, it will go into quantum mechanics, but we have not started even the
Okay,
main
sir.
part. Yeah, I will tell you. Okay.
So, I
So
think
what?
it's an operator. I mean,
It is an
IH,
operator.
cat, del T,
Absolutely,
Hamiltonian operator.
absolutely. It is an operator, quantum operator. Right. Okay. So you see here, this, if you go to this video of mine, General Relativity, what is classical system, importance and significance, I will send you a mail when I will be issuing the certificate. All those videos, links, I will provide it to you, because I don't have the time again to go back. So till now, what you have understood is that a spontaneous emission is something which is non-classical in nature, and a classical system cannot define that. And also we understood that Schrodinger equation is highly classical in nature, because it predicts the future behavior of a dynamic system, where it will be. And if it predicts the future behavior, and something which has got no future, which we just saw in this equation, this part, this one, this has got no equation, no future. So that is why Schrodinger's equation is classical in nature. Okay. Now I will come to what is the evolution of special relativity. So I just wanted to quickly go through the slides. So special relativity actually started with annus mirabilis, that means miraculous years of Albert Einstein. So four equations, four mathematical theories were published: photoelectric effect, Brownian motion, theory of special relativity, and mass energy. A common question to all of you: for which of these Einstein won the Nobel Prize?
Photoelectric.
Photoelectric effect.
Photoelectric effect.
Photoelectric effect.
Okay, great. Okay. So here you see, this was actually the development of special relativity. Isaac Newton theory, then it was Galileo Galilei's, I will say, Galilean transformation. People thought there is something called the ether, and even Maxwell framed the equation thinking that there is something called the ether. And then Michelson-Morley's experiment removed the concept of ether. Now here is a small, very important story. We know Lorentz actually framed what is called Lorentz transformation, Lorentz boots, etc. But it is basically prior to Lorentz, this particular person, Henri Poincaré, Henri, I mean to say it's a French kind of a pronunciation. This person actually found something which is called a Poincaré group. Poincaré group, okay, GROUP. And this actually showed similar things like Henrik Anton Lorentz. Okay, but as you know, history doesn't always account for great achievements. So Poincaré's group was not taken into account, and later actually Henri Poincaré's thing was taken up by Albert Einstein, and he formulated using Lorentz transformation special relativity. Okay, here is a quick question to all of you. Honestly tell me, are you enjoying this half an hour till now? I mean to say, is it all okay, or are you feeling bored?
Yes, sir. Absolutely.
We are enjoying hearing.
Yes, we are enjoying this.
Okay, great.
We are enjoying, sir.
Okay, great. Now here you see, this is basically the problem. I always try to tell my students that first you need to understand what is the problem. Suddenly we make a special theory of relativity. Suddenly Newton came into this thing. I mean to say, what is the problem of the earlier theory that this theory came? Now don't take me wrong, I'm constantly taking Monica's name or others' name because she introduced herself as a teacher. Maybe there are other teachers. This is also a point to Monica and to other teachers. Whenever you are going into a theory, try to explain the students what is the problem with the other theory, and that is why we need a theory. Got my point? Mathematically, if I cannot do this, dear students, then I know Newton's laws of motion. What is the problem with Galileo? Mathematically show them that beyond this we cannot go. That is why we need Newton. Beyond this we cannot go. That is why we need Einstein. Things like that. So here you see the invariance of the speed of light. At one end, it told that light speed is invariant. That means no ether is there. Then how it will do with classical mechanics? Also, it was not clear that the consistency would reconcile with classical mechanics. And Michelson's Morley experiment has showed there is no ether. Now you see here the genius of Einstein. All these were happening. Michelson-Morley experiment told that there is nothing called ether. That means the speed of light is constant. That is why special relativity came into being. There are two reasons which I have not shown here. One is that if the speed of light is constant and there is nothing called ether, then the classical mechanics should obey that there is one speed which is constant, that is speed of light, which was not done by Galileo and Maxwell. Point number one. I mean to say, problem number one. Second is that Maxwell's equations, if they are actually showing electric and magnetic field, etc., So that will also go with the speed of light, that is photon. Then these are not relevant to each other. That was basically the problem, that in 1905 in the Swiss office at Switzerland, Bern, this is a very famous picture. This is the desk where Einstein used to work, and this is actually Albert Einstein, and he made this famous quotation: that worldly cloister where I hatched most beautiful ideas. And nowadays you see people, my daughter and others, they will say, Baba, I need a nice home and a small place where there is no sound and AC is there and I've got a nice pen. So nowadays people demand such a lot of things. And think of Einstein sitting in that small table, and there is such a lot of noise, but yet he could formulate one of the greatest discoveries, that is special relativity. So the special relativity actually comes with what we call two things. One is that the laws of physics are same and the speed of light is constant. Now, when I say that the laws of physics are same, what do I mean by that? Does that mean what I am seeing and you are seeing is the same? I will show you in the next part of the webinar. Okay. Now let us try to understand this thing, which is
I
called
have a
the
question regarding this.
yeah, sure.
So,
Tell
as you
me.
have said that STR means the special theory of relativity has discussed about two concepts mainly, and
Mm-hmm.
the speed of light is constant, the first one, and the
Mm-hmm.
ether. So, what are you
Hmm.
say? Like the ether concept was discovered earlier, rather means special theory has just
Very good question.
proven
Very
it
good
wrong.
question. No, Michelson-Morley's experiment was made in 1887. Earlier, it was discarded. Means people came to know, okay, there is nothing called ether. So if there is nothing called ether, that means the speed of light should be constant, because ether is a medium through which if the light goes, it will either become slow or fast. Okay, Ayushi? So after the Michelson-Morley experiment, we came to know there is nothing called ether. That is true. That is nothing called ether. Then Einstein took it up. So if there is nothing called ether, then the fastest speed on earth is the speed of light. So the speed of light should be constant. And if the speed of light is constant, then all the laws of nature would happen accordingly. Is it clear, Ayushi? Tell me.
Yes, and now clear.
Okay, good. Okay, second thing, this one which we are talking about. Yeah, Omar, you have a question.
Yeah, sir, I have a question that is there any relativistic equation for Maxwell's equations?
Yes, I will show you. Very good guess. Thank you very much. Yes, there is a relativistic equation which we can derive, but I'm not showing the derivation. This is the equivalence principle. What is the equivalence principle? Right now, I'm sitting on my chair. The earth is actually giving a thrust. So I am feeling the weight. I mean to say my weight. Maybe I'm now 100 kgs. I don't know. So this is the weight, right? So the earth is pushing. I am there. So this is the weight. Now imagine the same thing, that you are in an outer space or on a elevator lift, say for example, and the lift is going up. The lift is actually going up. So what is happening is that the lift is going up, the same thrust is on your feet, just like right now you are sitting, Jubin is sitting, Uttam is sitting, Ayush is sitting. So you feel a thrust on here. Same thrust you will feel in outer space. Say for example, if there is a spaceship and the spaceship is moving up, you cannot see outside, you cannot see anything, you cannot hear, etc. So what Einstein thought, this was actually 1905 at the Swiss office, that if, say for example, if I'm sitting over here and there is a thrust which is giving into me, and the same thrust, if it is being pushed upwards in an elevator, both of them are the same, both of them are equal. That means gravitational acceleration and the force which is pushing me up right here, these are the same. Again, on the same way, if I'm falling down, my God, I mean to say, God forbid, the floor collapses today and I start falling down. Okay. The whatever I will feel, same way, if I am moving down an elevator and the chains of the elevator, may God forbid, it does not happen. The chain of the elevator is moved up and I am also falling. What will I feel? Both this same thing. I won't be able to feel the force. It is just I am free flowing. That means what? That box, and this part you can see, the boxed stationary in gravitational field is equal to the box which accelerates in empty space, and the box freely falling is equal to the box which moves through a speed at constant velocity. Again, you might say that how this can happen. No, this is a guess. This is what is called a thought experiment. In German language, it is called a Gedanken. That is a thought experiment. Now, this was very significant in the development of general relativity, that if gravitational acceleration box in a gravity field is the same as that the box is accelerating upwards, that means that there is nothing which can be called as a gravity. So here you see, I would like to show you that this one as this one is the
Sir,
same.
I have
So
a question.
yeah, tell me.
Sir, I have a question. Sir,
Yeah.
when if an observer is falling downward
Hmm.
with a constant velocity, then
Hmm.
as if he is accelerating downward, these are the same thing. Thought experiment actually what tells us, I mean.
If I am moving on a free space when there is no gravitational acceleration, and if I'm moving same in the outer space, it is all the same. These two are the same thing.
Okay,
Okay.
sir.
Yeah, Ayushi, you have a question?
Yes, sir. Sir, just as you have said that, like new means speed of light, and sorry, the moving velocity as constant
Mhm.
as the gravity doesn't work, right? So the
Mhm.
same concept was discussed by classical mechanics and Newton, well, by Newton, and in special theory by Einstein. Means they both have discussed the same concept. Like
Yes,
according
it was
to
discovered by the
Einstein, if we'll
same
talk about.
concept. Yeah, yes,
Mhm.
but it was Newton never thought that there cannot be anything which is called a gravity. Newton always thought gravity, which is called an action at a distance. Newton, this is a very good question, Ayushi. Newton knew that there is gravity as itself. I mean to say, it is not a force. He could perceive that in the later 80, 79, 80 years of his age. He thought that gravity is not a force, but what it is, he cannot calculate. But what is thought it called is the action at a distance. Something is pulling something, but it might not be a force. This kind of a intuition he had in his mind. Okay. Okay, so you see here, that means if I am shining a light ray, here is a light ray, okay, which is shining. And if this lift is going upwards, then you will see that the light ray will be something like this. Try to imagine, this is the lift, okay, accelerating upwards. And if I throw a light from the window, so this is the window, okay, and I'm throwing a light. Instead of light coming here, as the lift will move upward, the lift is moving in this direction, the light is coming from here. Instead of moving there, the light will be bending here in this way. It is bending down. That actually made Einstein think that if light which is shown, which should be in a rectilinear motion, because Newton told that that light travels in a straight line. Now if this light is moving in this direction, this direction, this way, then what is the problem? What is happening that the light is traveling in a bent space? That is what is called a space-time curvature. Einstein found that, you can imagine this, for example, this is my finger, right? It is, light is coming here, and it should be going like this, but as it moves, the light, bends like this. That means he could understand from there that the earth, either the earth, we have already proved that the earth is not flat, but what is more important, that the space or the area where the light is moving is also a kind of a bent, because the light is not moving in a straight line. The experiment showed that if I shine a light, it will go down, it will bend like this. Is it clear to all of you? Jubin, Ayushi, Junaid, young people, those who can understand? Okay. Now, this is the reason that Einstein thought that I should unite space and time. Somebody was asking me just quite a few minutes before that, space and time, how it is related. He united this to space time. Now, look here, I need to quickly do, because there are a lot of things. It's already 8:50. Now, I don't have any rush. If you are all okay with this space, then I'm fine. Maybe you have to go to dinner, etc. So, for Isaac Newton, this time and space, all the physics were taking place here: motion, momentum, torque, motion, gravity, everything. And space time was actually described by three-dimensional Euclidean geometry. Time is time, space is space. Right? Now you see what happens here. Einstein generalized this to one single thing, which is called a space time continuum. The question is that why Einstein generalized space and time? Suddenly, is it that it came into his mind that space and time should be into one space time continuum? No. First reason is that this. Now you see that the laws of physics are the same for all observers. If that is so, if the laws of physics are same, then say for example, this is time and this is space. So if the laws of physics are same, then I can, will I observe something in space and something in time differently? No, because there is nothing itself called space different and time different. Einstein united it into what is called a space time. Clear? Second thing is that the speed of light is constant. So if I am up to travel at the speed of light, you would not experience any passage of time because it is all very fast. So if I cannot experience anything like time, then how can there be a coordinate called a separate coordinate called time? Also, we will look into later that geometrical description of gravity is not a force, but it is a curvature. So these are very few important points which we need to know in order to understand that why Einstein united space and time. But yes, there is a reason. Omar bin Abdul Aziz actually asked me a very good question, that is there a relativistic. Now you see, this is something very interesting. James Clerk Maxwell's equation, which we read today in our college class or in our research, is actually a set of 20 original equations. Why? Because I'm now coming to answer Omar's question, and all of you will understand. So these 20 questions, the original equations, were actually reduced to 4 by this gentleman, Oliver Heaviside. It's a very interesting history, and if you want to know, you should watch this episode of mine. I will mail all of this. This is called History of Maxwell's Equations, and this actually tells that how Oliver Heaviside originally from those 20 equations came down to what is called Maxwell's 4 equations. Why I am telling this? Now Omar, here is an answer to your question. These are originally the non-relativistic equations. Okay. Now, these equations were made relativistic using this one, F mu nu. This is actually called the tensor form. Now, the question is that why Einstein made it. I just was talking to Anirban. I told him that if the speed of light is constant, and all the nature, all the laws follow the same frame of reference, question is that then obviously Maxwell's equation has to follow the laws of nature, which is the speed of light. So classical mechanics has to marry happily and stay together with relativity, because special relativity is talking about speed of light, and electromagnetism, photon emission, these are all related to speed of light. That means that this Einstein's equation, the Maxwell's equation, if they're united together with special relativity, we get one complete theory. That means special theory of relativity is highly, cannot join again. I don't know. Both these equations are taken together, and that becomes one complete theory, because Einstein, when he formulated this special relativity, he was in the target that I have to unite electromagnetism together, because without electromagnetism, without the speed of light and movement of photon, how can I describe the physics? Is it all clear, Vinay sir and others? Are you all getting my point? Ayushi,
Sir,
Junaid?
So why Einstein used to unite
Yes.
all these theories in one single thing?
Simple. The reason is that if Einstein's special theory of relativity is something which is talking about the speed of light, and just a second, if somebody is talking about the speed of light and how in different frames, inertial frames of reference, things will move, Maxwell's equation, Ayushi, was the most important equation during that time. Apart from Newton's laws of mechanics, anything that would support electricity, magnetism, that was only Maxwell's equations. Now, try to understand, Ayushi. Newton's laws of motions were expanded by Einstein's special relativity. Then what to do with Maxwell's equations? If you can unite Maxwell's equation with Einstein's relativity, all things are done. Galileo is already done. Newton's laws of motions are already done. And what is left? Only Maxwell's equation, electricity and magnetism. Are you clear, Ayushi? That is why there was a reason.
Okay, yes, sir, clear.
Yeah. Okay, Omar, your question, please.
yeah, sir, we know that A special theory of relativity is not the tensor based, but we
No, no,
here.
no, no, no. Yeah, actually,
Yeah,
you can use tensors in special relativity. You check my lectures, you contact me later. I will show you. There are a lot of tensors in special relativity. I mean to say, it was not Einstein who used it. Later, it was developed. That is called
yeah,
Faraday
yeah,
tensor.
yeah, yeah,
Then
sir.
there is electromagnetism. There are a lot of tensors. Now, why I showed you tensor? Because tensors reduces lot of big equations into a small equation. Are you getting my point? Okay.
Yeah,
So
these are the
Lorentz
partial differential equation actually.
partial
So
differentials, yes, absolutely. We can do that, not a very big problem. I have done a lot of derivations through tensor, not a problem. Okay, so now the question here is that what do we mean by equation is relativistic? Here I would again come to Ayushi's question. Very good question. Ayushi was asking what was the need, why did he used it? Now you see the reason. Now let me show you here. These are the Ayushi. Pay attention. These are the Maxwell's equations. Okay, these are in a non-relativistic form. Whatever, electricity, magnetism, Gauss's law, whatever. Now, say for example, the same laws I am moving. I am doing it in a Lorentz transformation. That means I'm not going to explain Lorentz transformation again, it will take time. Say, for example, this x-axis has moved into this x prime, and this t prime has moved into t prime. That means the coordinates have changed. Okay, Ayushi, the coordinates have changed. Now, my question to you is that if all this magnetism, etc., whatever the things, if they are actually taken into this coordinate, which is a changed coordinate, will it show the same result? Remember that the basic special relativity tells that the laws of equation will be same for all observer. So my question to you, Ayushi, is that if this happens in a non-relativistic frame, which is our Newtonian laws, then if I move the frames of reference, this is going this, this is going this, this is going this, these laws of frame, will it show the same thing?
Yes,
The
sir, I think
answer,
it will.
yes, the answer is a big yes. That is why Einstein united Maxwell's equation, because if things starts moving, and moving at what speed? C, the speed of light. If things starts moving at the speed of light, my question to all of you is that we need to have electromagnetism or Maxwell's equation should follow the same law, should give us the same result. Will it give us? Yes. And that is why Einstein united relativity with Maxwell's equations. All clear? Very clear? Overall, all
Yes,
of
sir,
you clear?
clear.
Yeah. So that is why this is the reason that this union one was done. Now remember, we could also have done this equation with Galileo. Galileo also had a Galilean relativity and Galilean relativistic transfer. But no, we cannot do this. This is wrong. Why? Because we find when we use mathematics, I have not shown this, when we use mathematics, what we have found is that if we try to transfer Galileo's law or Galilean relativity to Einstein's law, we get something which is called greater than the speed of light. And this is not done. We cannot have anything which shows greater than the speed of light. That is why Galilean laws are not going ahead with Newton's laws. That means we cannot transfer Galileo's law to relativistic equation because it shows v plus c. That means the velocity is moving greater than the speed of light. All clear? I mean to say, is it going too heavy or is it boring or you're enjoying? I keep on asking this to my
So,
students. Yeah, tell me, Ayushi.
sir, I want to say that the Galilean transform means Galilean concept was trying to say if it I have told about the velocity means the speed of light should be greater in that case.
No, no. I am saying that if I use Galileo's equation into relativistic equations, then we get something which is called a greater than the speed of light, which is wrong. That means the equations are not properly getting hand in hand with relativity. If you go to v plus t, c has this one. This is basically called Galilean transformation. So if this is a Galilean transformation, if we put those equations which I have not shown here it will show that something is going more than the speed of light, which is not done. That means it says that Galileo's law are not transformable to special relativity.
Can
Okay.
we say like Galilean has haven't drawn their equation which follows the special theory of
Yeah,
relativity?
obviously, because Galileo was never aware about anything which is going more than the speed of light. Even Newton was not aware. So anything moving at the speed of light fails with the equations. Okay. So here is a summary till now. General relativity is more than geometry rather than mathematics. The bending of light, Alessandro research, does that mean that Lorentz transformation arose from electromagnetic effects? Yes. Yes, I can. You can say that. That is, I mean to say, not typically it arose from that, but yes, Lorentz transformations are actually a part of, I would say, electromagnetism, because only if you saw, see, Alexander, the laws of electromagnetism, once they get transferred, we get this root over 1 minus v square by c square. That means the velocity should be moving equal to the speed of light, and this was not happening with Maxwell's equation. So you can say, Alessandro, in this way, that Maxwell's equation, hear me out, in order to make Maxwell's equation relativistic, we need Lorentz transformation. So in one way, Lorentz transformation actually arose from the electromagnetic effect. No, it arose from the need of uniting electromagnetism with special relativity. Clear, Alessandro? I think you're joining from Peru. So
Yes.
the need, yeah, the basic need to unite special relativity with Maxwell's equation arose from electromagnetism or Maxwell's equation. Great. So here we go from flat space to curved space. This is now we are going into, Ayushi is asking, sir, you have before in previous videos that time is reversible, linear Schrodinger equation, can type something like that, can you please clear it? Okay, I will come to that part later. It's already 9 o'clock and we have to cover up a lot of topic. Show how much. Okay, so here you see that when we go to the curved space, there are two laws of relativity. We have to keep it in mind. That means what? That means actually we have to keep these things in mind, that these are basically what are called the formulations of relativity. First is that laws of physics should be actually independent of observer's motion. That means what? That if this observer is moving here, say observer O, and this observer is moving here, observer O prime, whatever happens, the laws of physics should be same. I will tell you what it is. And equivalence principle, this was what I showed you, that gravitational acceleration is the same for all observers in gravitational field. Okay, here is a diagram, a little bit mathematically, things will be very easy. Now here you see what I have done in a flat space time. If I draw a vector, something like this, how will I measure the vector, Omar? Simple, I will add the components of the vector, this component and this component. Okay, now say for example, I am moving this flat space to what is called a curved space, this one. Now you see the vector remains the same. Can I select a different color? Let me see. No, let us not waste time. So the vector remains the same. This is the vector. Okay, the vector remains the same. Yeah, I think it is here. Yeah. So the vector actually remains the same. Now you see there is some kind of a change, that these components becomes longer. This one a prime y, see, it is bigger. A prime x, it is bigger. So that means what is happening now, pay attention, from flat space we are moving to curved space. The components of the vector starts changing, but the vectors remains the same. That means something has already started to change when we are moving from special relativity to general relativity. Here also I rotate, you see this one becomes bigger, this one's becomes shorter, this one becomes bigger if I rotate it. So here you see that from flat space to curved space, if I try to move, then what is happening is that vectors are good enough to describe the laws of physics. But in a curved space, these vectors cannot take place. Immediate question is that what would I need in order to mention what is happening in a curved space? You see this one. This is again a very basic idea that all these are Newtonian law. All Newton's laws of motion. These are okay with flat space-time. Newtonian mechanics operates in a three-dimensional. Vectors can be described using coordinates. No problem with that. Vectors can be described to use coordinates. Now you see here that if I am moving from a flat space to a curved space, I cannot use the Pythagorean rule. I need something which is called a metric tensor, because this is not a straight line. There is no angle. There is not an isosceles triangle. If I try to plot a angle, a triangle over this, it will look something like this. This will come like this will go like this, and it will go like this. Try to plot, young people, maybe others, Monica, Alessandra, Jubin, try to plot, get a soccer ball and try to draw a triangle on a soccer ball. Maybe tomorrow is Sunday. See what happens. It will show like this. So from here, we find a very big problem, which I was telling to Monica just before that, and to other women who would be who are watching this webinar today, that this actually created a problem. This one actually created a problem. This curved surface was unable to explain the Pythagorean law. Rohit Asha was telling Euclidean, non-Euclidean space, yes. And the problem was at the University of Göttingen in Germany, and the year was around 1915. We are going a little bit fast forward. Einstein's general theory was already published, and the problem was with a very big problem which even Einstein cannot solve. These three gentlemen faced a problem. The problem was that general theory of relativity was not following the laws of conservation of energy. What do I mean by that? I will come to that point. It is related, I won't say difficult, but it is very deep. I mean, it is a little bit philosophical, and deep thinking is required. So David Hilbert, Felix Klein, and Albert Einstein was unable to solve that the law of conservation of energy seems to violate using the equations of general relativity. They called, who is called one of the greatest, I would say, physicist mathematician born, Emmy Noether. Now, before I go to Noether's theorem, I would like to explain you something like this. What is this? Can anybody tell me this part, this equation? What is this?
That is okay.
Yes, sir.
What is okay? Okay. So here you see, earlier you can see my mouse. Now it is not visible. Is it something like that?
No, sir. Actually,
No,
it
sir.
wasn't visible from the beginning.
Oh, okay. Okay, fine. I'm so sorry because I am using this mouse. Maybe I don't know. Maybe whatever. Okay, fine. So you see in this slide, what I'm trying to show you is that if I get a comparison in term of a vector, how will I know that this vector is bigger or smaller than other vector? Simple. This one, the black one is bigger. Then this one is smaller, etc. But you see, if I am trying to, okay, let me just a second. Just hold on for a second. I will use the Jamboard. I think that is visible. Okay. Uh, Create a Jamboard. Okay. If I try to parallelly transport a vector from here, if I move around here and here and here and here, and when I rotate and I come back, what I see is that the original vector and the same vector are overlapping. It has gone here, 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 and then again it has come back. This is what is the actually the problem with Noether's theorem. Okay, let me now show you my slide. Mm, uh, Again, I have to go back to share. Where is the screen? You cannot see my screen, right? Just a second. Hold on. Hold on, I don't know what is happening. Just a second. To share. Hold. Where is my screen? I need to go to share window. Aha, it's a problem. Just a second. share screen window. Yeah. Okay, so here you see this is actually what is called a parallel transport. Parallel transport means we have parallelly transported and the yellow vector has come back to the red vector. Okay. Now here you see this is actually a problem. Try to understand a little bit closely because this mouse cursor somehow it is not working. Now you see on the left hand side the sphere, all of you please you can say me yes or no. Now you see the yellow vector standing on the sphere, the black person. Okay,
Yes,
Rohitasha, is it
Yes,
visible
sir.
now? Okay. Now, if I
yes, sir.
start
Yes.
moving this yellow vector on and on and on and on, and it goes down, it goes to purple, and then it goes back, you see there is a difference. The difference is that yellow vector and the blue vector are actually not the same. Okay, that means the vector you get around it basically does not make sense because about the total amount of energy and momentum. That means, say for example, there is a surface. Now this is a little bit, I won't say difficult, it's a little bit confusing. If I have got a surface, okay, where all the physics is taking place, for example energy, momentum, force, etc., are you getting my point? Now if that surface is uniform, I mean, it's a flat space. Okay. So whatever the vectors, etc., and the momentum, energy, whatever is happening, if I start drawing those vectors in one point, etc., etc., this earlier slide, it will come back. That means the energy, momentum, Newtonian mechanics, whatever is taking place at that place can be taken a sum total, and we get the conservation of energy. That is the total sum of energy, momentum, etc. Okay, now what happens really when the entire space is curved? What happens when the space is curved? Can we really add those? No, we cannot add because the space or the place where those things are happening itself has got a bend. It is already bending. That means the vectors, which are actually a summation, we cannot sum them. Say for example, this is force 1, force 2, force 3. We can add together and we can say that the total summation is say Fg, which is a summation of these forces. But how can we add those forces if the space-time curvature is bent? That means the forces, if we add the vectors together, the vectors are changing because you can see that the yellow and the blue vectors are different. Are you getting my point? So here you see in this slide on the left hand side, you can add all the vectors and then sum up. Vectors means different energy, momentum, etc. But on the right hand side, you see there is no way to get back to the original vector. So why? Because if you want to get them together, you would bring them to the same point. But since the quantity you get depends on the path you take, that is why it is not well defined. Any question regarding this quickly? Are you getting a basic idea of Noether's curvature? I mean to say, any question, anything you are not getting? I know it is a little bit, counterintuitive. Alessandro got it. Okay. Jubin, Ayushi, Monica, Rohitash. Okay, fine. So that is why
Yes,
there's the
sir.
problem. Classical mechanics, special relativity, we can get energy conservation by adding the total momentum. Read the line below. I don't know why my mouse is, betraying today. It's very bad, of a specific place in relativity, but in case of general relativity to the curvature, there is no way in which we can add the vectors together. Even if we do, we find the vectors pointing in different direction. This is a very important concept. All of you, please do try to understand. This parallel transport will be very useful for you. So here you see that the law of conservation of energy here is not conserved, because if you take a small place, I mean to say curvature is very less. Okay, that energy coming in and the energy going out, is it all okay? But the moment we take a big curvature, which is the soccer ball, okay, the effects of curved space-time starts to play a role and things starts to become very complicated. Noether's theorem is a very complicated topic. Very advanced mathematics is required, but I am trying my best today to give you an idea. So how do we solve it? Actually, Noether came through a theorem, which I'm not going to explain it. So that was a question that if photons travel through an expanding universe, The photon starts with a very high frequency, then it become bigger and bigger and bigger and bigger and bigger. What does that mean, Jubin? Does that mean that we are losing some amount of energy? That was the question with Einstein. Are we losing the energy? If we are losing, then it is violating law of conservation of energy. Where is the energy going? So if you want to know more, just go forward through this theorem, this video of mine, which explains a lot about Noether's theorem, the problems, etc. And I think you can get an idea. Everything okay till now? Are you there all with me?
I have a question
Yes,
regarding
sir.
these.
You should tell me. You can put on the camera because I have never seen you. Okay, yeah, tell me.
The first question is how Einstein came to know and how have discussed first time about the curved space rather than like flatter space.
First of all is the bending of the light. That was basically the curvature. I told you that if the light is emitting, then instead of going straight, the experiment showed that the light is bending down. And the curvature, if you're talking that how the curvature actually happened, that came actually through Einstein's field equations. But Earth is definitely curved. I mean, it is curved in the sense it is not flat. That is actually known right from the beginning. But gravity is causing the curvature. That was actually what we are now starting. That is what is called a manifold. Okay, we will show you now. Now we are now going to the last part of our webinar where we will discuss about Einstein's general theory of relativity, the curvature of spacetime, which Ayush is asking. And till now what we have learned about the evolution, special relativity, Noether's theorem, what caused the Noether's theorem. And remember, to Ayushi, Monica and other women, this was I was talking about. So this lady, Emmy Noether, actually, was never paid the salary. She was never recognized, but she is the woman who actually saved Einstein from, getting into problem, general theory of relativity. So please learn about Noether's life, about Noether's theorem. This is my request. She is one of the greatest physicists. In some way we can tell even better than Einstein, because Einstein did not knew how to solve this law of conservation. She came and saved the entire ship of general relativity. Right, Ayushi, Monica and other women? So take it up as something very motivational. Yeah, Rohitasha, your question.
So we can easily visualize a curvature in space, in 3D space,
Yes.
but how can we visualize curvature in space-time in 4D? How can you visualize
No, no.
that?
So it is simple. Don't think time to be a separate dimension, Rohitasha. Space and time is all one. So if it is one unit, then it is curved. Time, if you take as a separate dimension, draw it on a piece of paper and curve that y-axis, x-axis in this direction. So it will become curved space. Time curvature is a conceptual idea. I mean, it is a physically time is nowhere curved. But we put together as space-time together as a curvature of space-time.
So we can say that it's a new space. Space-time is another space, you can say.
It is a new space, it is a new concept, it is a new identity. Okay.
Okay.
So we now go to what is called a manifold. Now, manifold is something which I want to tell you. Manifold means a surface. Can you see my hand, all of you? So this is, although this is not a manifold, but if I draw lines around here and there, etc., what I was showing you over here, this figure, this type of a curvature which you can see on the soccer ball standing, etc., these are actually curvatures, but we cannot call it a curvature. We have to give them a proper mathematical name, which is called a manifold. Manifold means many-fold. Okay, but here you see manifold is actually something a little bit different from a fold. It means that every point in a manifold has a small area which looks like locally Euclidean. What do I mean by locally Euclidean? This is the wall. Okay, try to see this. This is the wall where I am sitting. Okay, now if I zoom out from this wall, go outside and outside and outside into the space, this wall will not look like straight. It might look something like different. But if I zoom in this wall, I can get a straight line as a straight line. I can get a triangle as a triangle. Okay, that means manifold, just like my hand, is a curvature. It is curved, it is bent. But if I zoom in, it will look like a wall. It looked like a local Euclidean flat space where we are doing all the algebra, trigonometry, and basic mathematics. Are you getting my point? That is why I've written on the left hand side that every point in manifold which would look locally Euclidean. Locally Euclidean means what Omar was telling, locally flat space, where we do the lines, straight lines, etc.
Actually, it is locally two-dimensional.
Locally two-dimensional, absolutely. Now here you see on the left hand side, this is global. The person is moving. If I zoom out and try to watch from above, it is global. But if I try to zoom in and see, this is local. Now you tell me why I am trying to get into something local. We are all going into cosmological scale, black holes, etc., space-time curvature. Why I am trying to do local? The reason is that I want to do local so that I can use calculus. I can use mathematics. If I try to take into global scales, mathematics won't work. It will work, but that is what is called topology. But we are not taking into account topology right now. So here you see, can you see the left hand side, all those things? These small boxes, what are those? These are differentiation. So if the lines meet together, it is a positive curvature. If the lines are parallel, it is a zero curvature. If the lines are diverging, they are negative curvature. And each of those spheres can differentiate. I can divide into small pieces, and I can use calculus. So any surface which Omar was telling locally looks two-dimensional and I can use calculus is called a manifold. Now can you relate that to Einstein's relativity? The space-time is curved, but will curvature help us? No. We have to use mathematics, we have to use calculus, we have to use differential geometry to measure the curvature. Ayushi was asking how Einstein measured. This is how he measured. So here you see, if
Means
I
we can
zoom,
say like at
tell me.
it means we can say at microscopic level, all the
Microscopic and
flat
macroscopic.
space
Yes,
are
yes,
overlaid.
yes. So you see here, if I zoom it, it will become a straight line and something like that. So here I would request you again, I have made an exclusive video which is how differential geometry shaped general relativity, lesson number 22. You can go to my playlist in differential geometry. You can see that here actually I have spoken about how differential geometry is related to general relativity, and manifold etc. are all nothing but differential geometry. That is, I always tell my students who are really serious, who wants to learn general relativity, first should learn differential geometry, and before differential geometry should learn the basic high school geometry better. Who coined the term manifold? Bernhard Riemann. Manifold, that was done by Bernhard Riemann. He was a very poor person. His father actually spent all his money to go to Göttingen and work under the very famous, world famous mathematician Carl Friedrich Gauss. So he actually worked on what is called the foundations of geometry. This is the book which actually, I would say, gave birth to a manifold. And he actually found what is called a manifold on 10th of June 1854. When his dissertation was there, he contributed and made the term manifold. Okay, now we come to the next important concept. What are tensors? And I will show you why we require tensors. You know, Einstein's field equation are all. Now, you see, we learned manifold right now because these tensors will work on manifold. That means the curvature of the space-time will be measured by tensors. And where are the tensors happening? On the manifold. So here is my hand. Everything is happening in here. I measured this. This hand is the manifold, and all those curvatures, etc., are used by calculus. And this is the discipline called differential geometry. And what is going to measure this? Tensors. So I quickly go through. This is actually called a stretching information. That means if there is you can see this sphere on the left hand side. All of you can see the sphere with the red one. Yes or no? Clear? Okay, so if this
Yes.
sphere, if this sphere gets stretched, remember, just imagine, that is why you told at the beginning, intuitive. Imagine a ball. Now stretch it. It will become something like the right hand side oblate spheroid. So the information over there will also get stretched in coordinate. Now, question to you is that, maybe Suhail or others, is that if the information is stretched, how I'm going to measure? Because I have lost the information. Not lost, but it has been deformed, it has changed. That means our normal vectors, etc., won't be able to measure this stretching information. It cannot, because vectors operate on a straight surface, and here it is a curvature. So vectors cannot do that, normal equations cannot do that. So we need a something which can measure that change, that measure that stretching, and that is why it is called a tensor. So you'd see tensors are vectors, but vectors can only have magnitude and direction. Remember, magnitude and direction. But here it also tells on which surface it is happening. So if you see a cube, I can say the force and direction is in this way, but it is also happening on the right hand side, on the upper left hand side, on the below the cube. So that means it is something more than vector. It is giving not only magnitude and direction, it is also giving on which side. So that is why you see tensors actually started using the crystal structure. I will show you, because you can imagine crystals have different shapes. Have you ever seen a crystal? Anybody? You see there are different types of shapes. So
Yes,
I
sir.
mean to say, yeah, you
Yes.
can see it is up, down, and different sizes. So if I measure a stress or a strain, I need to know also on which side it is happening. So this is a quick idea that how tensors came, Cauchy, then Hamilton, Joshua Gilbert, etc. Here you see these are basically, I want to skip this because you can join my tensor class where I can deal with this better. Rank 1, rank 2 tensors, etc. Here it is, the crystal structures. How can I use those crystal structures? And that is why tensors came into being. Okay. Now here you see this is very important. A person is throwing a ball on the left hand side. Okay. Now I rotate that axis on the right hand side. Again a person is throwing a ball and I stretch that axis on the right hand side below. So the question is that how am I going to measure the laws of physics? Throwing a ball, jumping, eating, dancing, whatever event of physics is happening, and if the coordinates are rotated, stretched, how can I measure that? Because Einstein told that the general laws of nature must be expressed by identical equations relative to all other system, whatever way they are moving, whatever the way they move, but the equations or the laws of nature should be expressed by identical equation. That is why we need tensors, because you have seen earlier, I have showed you the stretching, bending, etc. That means the vectors remains the same, but the coordinate or the components are changing. You are silent, I cannot understand. Are you getting me, or it is too difficult for all of you? I mean, so you can always respond sometimes by chatting or telling me.
Yes, sir.
All of you clear? Okay.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay.
Can you repeat it once again? How it is expand?
I am saying that in the case of the laws of laws, if the axis is rotated, of the axis is stretched, whatever it happens, why it is rotated? Because we are now in a space-time curvature. But the laws of physics has to be the same. How this can happen? How it can happen that the laws of physics we can measure, although the axis is rotated, stretched, bent, etc. Okay, so that is why we need something which is called a tensor. So here is again my video where I have exclusively written about tensors, a beginner's guide to understand general relativity. You can look into this. So what do we understand from here? We understood that the objects that takes care of magnitude, direction and plane. Here you see the bold one, that we need, as Euclidean geometry are no longer applicable, what Omar has rightly told, Rohitasha has told, the tensors helps to measure the curvature yet maintaining the symmetry and invariant laws of nature. That means everything will be symmetric, everyone will be identical, but things will be bent, stretched, etc. Clear? This is also another video of mine which is called Beginner's Guide to Manifold. You can check. I have talked at length
Yes,
about
sir.
what is
Yes, sir.
manifold, etc. Okay, here is also a very good story which you can know, that Einstein actually never knew about tensor, because tensors are actually discussed in what is called differential geometry. Okay, so that is why Einstein was educated by Marcel Grossman, Michel Besso, and this is one of the manuscripts which show that actually Grossman introduced this tensor on the fourth manifold, and he educated Einstein to learn about tensors, because without tensor, Einstein could not frame his field equation. We are coming to the almost to the end of our webinar, but please do pay attention. This is very crucial. We will now say what Ayushi and others was asking, that how Einstein developed the equations, or what we can say, how we can measure the space-time curvature. This is central. This is what I think you have been waiting for almost a month or so, Einstein's field equations. Okay, just let me have a glass of water. Are you all doing good? Because many people have gone out.
Yes.
Yes, sir. We are enjoying.
Yes, sir, it is going interesting.
Okay, this is the Einstein field equations. Remember, it is a collection of 16 equations. We are seeing one equation. I will tell you. The left hand side says that curvature of space-time. We are talking all about curvature. How do we measure? The left hand side of the equation measures the curvature, how much it is bent. Now you might ask, what is the use? I will come to that. And the right hand side says that how it is bent. So if you take a trampoline and put a ball, heavy ball on your bed sheet right now, it will bend. Right, Anirban? It will bend if you put a heavy ball on your bed sheet right now. So what is bending? The matter is bending, isn't it? Right, Junaid and Rohita Shah, Monica, the matter is
Yes.
bending. So if the matter is bending, then first we need to understand that if I put a 20
Yes, sir.
kg ball, 20 kg ball on my bed sheet, it will maybe break, it will tear down. But if I put a small ping pong ball or a small ball, it is slightly going to curve. So the question is that what is the matter, how much is the weight, etc. That will be measured by the right hand side, and left hand side will measure how much the bed sheet is going to bend. Clear? Okay. First of all, let me tell you what are the constants so that you can get a very nice understanding. Lambda, this is a cosmological constant. I will later explain maybe in another webinar. These are also not. 8 pi, it comes from Poisson's equation. G is the
Sir,
gravitational
how
constant.
matter is bending? I'm not able to understand.
If, say for example, you imagine a bed sheet. Okay, if you're pulling a 20 kg iron ball on the bed sheet, will it bend? Yes or no? It will bend. So what is that 20 kg matter? What is that 20 kg ball? That is matter.
So the
Are you
bed
getting
sheet
me?
is bending, right?
Bed
The
sheet
bed
is
sheet is
bending.
bending.
Huh. But what causes the bending of the bed sheet? The
The
ball.
mass,
Huh.
the
So
ball.
that is what it is called matter. Matter means whatever we see around the earth. That is the matter. So if I put the
Maybe
ball
the
only, then the bed,
reason.
huh?
I mean, the reason is the ball. Because of the ball, the
Obviously, that
space is.
yeah,
Okay,
the
okay.
ball is, that is what's the matter. Okay, okay. These are the constants. Now here you see, I will try to tell you on the right hand side. First R is called the Ricci curvature tensor. I will tell you what these things are. The second R is Ricci scalar. The G is the metric tensor, and there is something hidden which is called the Riemann curvature tensor, and there is stress energy momentum tensor. 1, 2, 3, 4, 5. These are the 5 tensor components which actually measures the curvature, the bending, etc. And we are going to quickly explore what do those tensors components mean in a very easy non-mathematical geometric approach. First, Ricci curvature, Ricci scalar, metric tensor, Riemann curvature, and the stress tensor. Along with that, if you see all those things, this takes up the entire equation. That is why I first educated you on tensor, manifold, and now I am coming to this. Now you see why I was telling it was 16 equations. Mu nu are basically indices of space-time. I think Junaid was asking. Time, 0 is the time axis, y, z. Rohitasha, now you understand. This is what you rightly told, one new space, one new model. So 4 plus 4 plus 4 plus 4, how much? 16. Right? Everywhere we have got mu nu, so we
Yes.
add up to 16. Okay? So it is a collection of 16 equations. Now here you see I'm just, if you don't understand, connect to me in my live class. Out of these equations, some of the components are very common. For example, 1001, 2112. In this way, the 6 component gets cancelled out. This is the it is a little bit complicated. I will explain you later. This metric tensor, 6 components gets cancelled out, and what you see is right below this g mu nu equals to, you see 1 2 3 4 5 6 7 8 9 10, 10 components, right? And in general relativity, metric tensor is actually what in Euclidean space, what you call time, distance, volume, curvature, angle. I mean to say, in Euclidean space, this is what the metric tensor captures. Yeah, Nirman, your question.
So why are you cutting the below component?
These are the symmetric components which get cancelled out, and we only get 10 components. 6 components out of 16 gets cancelled out, and we only get 10 components. Okay. So what it is?
So
Does
I have a
yeah.
question.
Mhm.
Why only the covariant indices are used here, not the
Yeah,
contravariant?
very good question. Here we are using the covariant components only because Einstein's basic idea of general relativity was to find a covariant theory of gravity. That means all the laws of nature will be same irrespective of whatever the way you, me, and others are moving. It's a very good question. I would congratulate Omar for asking this. That is why right at the beginning I showed you general relativity is a covariant theory of gravity, not a contravariant. That is why we are using covariant components. That means the laws of nature should match with the observation. Clear, Omar? Very good question.
Yes, sir. Yeah. Thank you.
Okay, so what does it measure? Now you see, this is what is measured. Ayushi, now you can pay the attention, you will understand. So Jupiter is very heavy. What does that heavy mean? That means the g is higher, means gravitational and acceleration. So if gravitational and acceleration is higher, that means the curvature is more, and if the curvature is more, that means it is very heavy. So heavy means what? Anything which causes a big curvature. You see, Jupiter's g is much bigger than Earth and Mercury's. That is why Jupiter is big. We say big like Jupiter, but Mercury is small, Earth is small. Why? Because the curvature is less, and the curvature is actually what? That is what the mass is. And what is mass? That is what Einstein's field equations is showing. That means that gravitation and acceleration g, if it is more, then curvature is more. If it is less, it is less. All clear? Let me quickly move to the other part. Please do respond, talk to me. I feel bored if
Yes,
nobody
sir.
is.
Thank you.
Yes.
Okay.
Yes, sir.
Yes, sir.
Okay, great. Now you see here I have just told you what are those components. So 0, 0, 1, 1, these are time and space and time and space and time and space. So 0, 0 is time, time. Okay. 1, 1 is space, space. 3, 3 is space, space. 2, 2 again is space, space. So it actually shows how time intervals are affected by gravity, how space components move in this direction. It is highly complicated, but because you are learning metric tensor, I thought to show you. This is 0, 1, 1. That means each of these indices, those who know tensors, each of these indices actually denotes time, curvature, gravity, which way, this way, that way, all those things. So here is the summary. Read only the bold one. They show how the presence of mass and energy not only affects the local curvature of space-time individually, but also how they influence each other, leading to phenomena like gravitational time dilation, etc. So this actually shows the interconnectedness of space-time in the presence of gravity. This is what metric tensor does. If you want to know more about field equations, you can go to lesson number 21. It only speaks about Einstein's field equation in much more details. Now, I told you this is symmetric. You see mu nu, the indices, if they swap with nu mu, they become symmetric. So now, Omar, I answer your question. Why we are using covariant theory of gravity? This is the reason. Simplicity. The symmetry of the metric tensor shows that there are only 10 independent components. Physical interpretation, symmetry of the matrix shows that the laws of physics do not depend on the coordinate. This is important. Do not depend on the coordinate. That means whatever the way, see, starting from special relativity, 8 o'clock we started, we now move into general relativity. Essentially, they are speaking the same thing. That is, the laws of nature would be same. That was in an inertial frame, and this is in a what? Non-inertial frame. And geodesic
Sir,
motion also.
I
Yeah.
have another question. In a contravariant tensor, we have also the symmetricity and
Yes. Yes.
the
Yes.
invariant nature. So why
Yes.
it differs from the contravariant? Why it is
No, It,
actually
it, it
contravariant is
really does no
used?
no it really doesn't it really doesn't differ in Einstein's equation. If you go to the equation, there are a lot of contravariant vectors, but the overall idea is to get a covariant theory of gravity. Otherwise, we won't be able to explain. It really doesn't differ. It is the same thing, but the overall nature should be covariant in nature. Okay. So this mu nu, this stress energy tensor which I'm coming, this is also symmetric. Symmetric means that it carries a lot of significance. It is simple. It will follow the laws of equation. Mathematics become easier. Differentiation becomes easier. That is why it is symmetric. Okay. We will show you what is a Ricci curvature quickly. This was actually the what you call the teacher of Ricci, the Gregorio Ricci, Tullio Levi-Civita later, and they formed this. And this is how it happens. So if I start with a point on the left hand side and try to move around, and then there is a point I try to move around, instead of two initial parallel geodesics will begin to deviate. It will begin to deviate, and this Ricci tensor actually shows how much the space-time volume change in this direction. Let me show you the next slide. It will become easier. Here you see, if I take a ball, okay, all of you getting it, yes or no? If I take a
Yes.
ball,
Yes.
if I take a ball and I try to move upwards, you see, in case of a positive curvature, the ball will shrink in size. You see, the green ball has shrunk. So this is what Ricci tensor does. That means if I move a volume of a ball around a curvature, will it shrink or will it grow? The change in volume, this is called volume element. I am not going into again that is again mathematical and complicated. I have shown it in my video. You can check it. Here you see, if I take the first left hand side, there is no change. That means Ricci curvature is 0. If the ball shrinks, that means the positive curvature, Ricci curvature is greater than 0. If the ball deviates, then Ricci curvature is less than 0. Yeah, Anirban, tell me. Anirban, you have a question? Okay. So if you now you see these lines, what I called is basically called geodesics. And geodesics are simply the shortest line between 2 points. Simple. Straight line is a geodesic. So shortest line between 2 points. This is a very interesting video which I have recently created. It was a good lecture. A lot of people participated. You can look into this. How geodesics are actually coming from Newton's laws of motion. It is the second order derivative, d square x, nothing else. It is a very interesting video, very simple. You go and watch it. This is a live lecture, not a video, where I have shown that geodesics has relation with Newton's laws. Okay. So this is another one. Okay, what does the metric tensor shows? Let me go it quickly. Metric tensor actually shows the I would say causality. That means if I'm going from my home straight, then this is called the Euclidean metric, straight line. Okay, and if I'm taking around this taxi and I'm moving around the pond, this is another metric which is called G taxi, whatever it is. So you see here, if I get a vector, the red one, and if I try to expand the x-axis, I was talking about this changes in terms of coordinate. Now you see the coordinate. X is increased, Y is increased. If these things continues to happen, then we need to do in this way. So you see the mapping around the sphere is done by stretching component. That means if I get an unstretched piece of cloth, okay, here it is, and if I try to put around a sphere, So what I will do, before I put around the sphere, that unstretched cloth, I will take a measurement, I will do calculus and get the length and breadth. Now if I put it around the sphere, what will happen? It will stretch. So from the unstretched component, using tensor, I can move into the stretched component. And that is basically the mathematics which I have not shown here, that we can actually tell from this point to this point what is the distance, this point to this point what is the angle, not angle in Cartesian coordinates, but in. So that is what metric tensor does. It takes the unstretched information and patch it over the stretched information. So if I get an unstretched symmetric tensor, once it is put over the stretched sphere, we can do the calculation. This is a very popular and a very good video I made 1 year back. So it is quite a long, it shows everything about metric tensor, derivation, etc. You can check. Okay, what is the Riemann curvature tensor? So you see Riemann actually, I have shown this, was a student of Carl Gauss. Okay, so let me skip this one, let me show this one. So this one you have already encountered, right? That if you are parallelly transporting, we come back to this. Now this is what Riemann curvature tensor does. The difference between the original yellow vector and the blue vector, how much difference it is. Are you all getting my point? This is what Riemann curvature tensor does. Now here is one quick catch. I have shown the movement along the clockwise. Now Omar might ask me, or Rohitasha might ask me, sir, what will it happen if I move counterclockwise? Are you getting my point? This is the sphere which is moving in this way. What if I move it in this way? It is going to be the same. You know why? Because this Riemann curvature tensor is also symmetric. Symmetric means in whatever way we move, the equation will be the same. And this is actually done by what is known as Christoffel symbol, which is the gamma sign. And Christoffel symbol is basically, I would say, symmetric. That means either this way or that way, it will be the same. Are you getting bored or you're getting frustrated? Lot of things coming up.
Yes, sir, we
So
are
we are,
getting it.
Yes,
if
it's
you
clear.
want,
It is very more interesting.
okay, this is the stress energy momentum tensor, right? Ayushi, the ball that I was talking to you, that the ball, if it is put on the bed sheet, it will curve. So this ball, how big the ball is, what it contains, this is measured by stress energy momentum tensor. Okay, let me now again a little bit go back and just quickly show you the Einstein field equation, then you will understand. So you see this R part is done, Ricci tensor, Riemann curvature tensor is done, metric tensor is done, C4 you know, H pi you know, what is left? T, that is the stress tensor. That is what I'm going to show you, how this stress tensor is actually helping you to measure the part. So here you see, this is actually what stress tensor shows. Now don't ask me what is, it is actually a tensor. That means all the energy, density, momentum density, pressure, etc., A, B, C, D, everything is here. This is one house which compiles everything related to matter. Nothing can be left. This 0001, I will delete later. So here you see the first energy density. Energy density, it is the energy that is responsible for the curvature. Pressure, responsible for the curvature. Movement of matter, responsible for curvature. So momentum flow and responsible. So all these things are responsible for curvature. So Ayushi, to answer your question, how much energy, how much momentum, how much stress, how much energy, how much pressure, how much, all these things are measured in this stress energy momentum tensor. So now you can see that Einstein's left hand side equation and the right hand side. So right hand side Ricci tensor, Riemann curvature tensor, metric tensor, all these on the left hand side. Clear? That is the curvature. And what is on the right hand side? Stress tensor. That means the ball. If I do not measure the ball, how will I know that how much stress, etc., it is coming? Are you getting my point?
Yes, sir.
Okay. So here you see that this, if this tram is moving in this way, this actually causes the curvature. This is what is known as gravity. It is called geodesic. Geodesic, as I told you, once I send you the mail regarding certificate, I will list out all the relevant videos, because otherwise it will go till 2 o'clock at night. My wife will be not happy, you won't be happy, your husbands will be killing you. So it is better that you read those videos, look into the videos later, right? So the object moves through space and time, and it creates what is called a gravity. Yeah, Rohitasha, your question, please.
So, sir, basically, this stress energy momentum tensor gives all the information about the matter, just like the
Matter.
psi in quantum
Yes,
mechanics.
absolutely. Just like a psi, it shows the wave equation, how the system evolves. This is stress energy momentum tensor, is about the matter. Yeah, Omar, your question?
Yeah, my question is that whether a stretch energy tensor is responsible for the gravitational force.
No, actually, gravitational potential is responsible. The stress energy tensor is responsible actually to create the curvature. Yes, you can say in some way, yeah. Yeah. I am just, yeah, you're right. Absolutely. Yeah. So here again is that one. Junaid, you have a question?
Yes, sir. Sir, so for dimension 4 sir, tell me what the value of curvature of space-time
I
for
cannot hear
each
you. Your
of the
voice is not
dimensions.
clear. Your voice is not clear. Can you come back a little bit later? I will just have few more things. Now, this is actually one of the predictions of general relativity. Now you see here, if I shine a light straight without the presence of sun, it's going to go straight. If I shine the light in the presence of a matter, which is sun, the photon will take the path of a geo. Remember, the photon is actually taking a straight line, the geodesic, but it is the curvature which is causing the matter to bend. Sorry, the light to bend. So gravity is the bending of space-time due to matter. Here you see, this is another very good video, mathematically also have given, does gravity affects the path of light? This is, now there might be a question to all of you, photon has no mass, but how it causes, but how it bends? It doesn't bend. Gravitational microlensing. Yeah, absolutely.
But it
Okay.
has momentum, right? So
It has
basically,
momentum. Absolutely, you are very right. It has a momentum, but it has no mass. When the question is that how it is moving, how it is bending, it is not bending. It is taking a straight line, but the path is bent, so it is it takes that kind of a path. So we come to the
Actually,
last. Uh-huh.
yeah, sir. Actually, a photon takes the geodesic of space-time, and that
Absolutely,
is curved in
absolutely,
presence of an
absolutely.
energy momentum stress tensor.
Absolutely. So we come to the last part, which is the black hole. As you see, the left hand side shows the space time is curved, and the right hand side shows the matter is curved. That means the basic easy thing is that if the matter is so heavy, if the matter is a 1000 kg iron ball, if I am putting it on my bed sheet, it is going to what? What is going to happen? The space time is going to split out.
crush.
Yeah, crush, and that is how it happens. So that was first predicted by this person called Schwarzschild, and he calculated what is called a Schwarzschild radius. That means anything. Uh, Mr. Prashant, if you can please mute yourself. Yeah. So you see that if this any body which goes below that RS Schwarzschild radius can turn into a black hole. That means you see the earth, the me, you, car, etc. Anything which goes below the Schwarzschild radius, that means I myself, I can be turned into a black hole if I can calculate, if my radius goes below the Schwarzschild. Every component has got a Schwarzschild radius, earth, mercury, jupiter. So if you can put it below that RS Schwarzschild radius, it will become a black hole. Okay. This is
Sir,
how
is
it
this
happens.
radius is
Schwarzschild radius.
sir,
You
this
can come
radius
back.
is somehow
Huh.
relatable to Chandrasekhar limit? You can say like
Very
that.
good question. No, it is not related to Chandrasekhar limit, but Chandrasekhar actually calculated prior to that what is called that Chandrasekhar Oppenheimer limit. Chandrasekhar actually calculated the limit which will be for neutron star. I mean to say Chandrasekhar's limit is actually what happens if this go below that. It was up till neutron star. Later it was taken into black hole. You are on the right track, Ayushi. You are thinking in the right way. So does the question is that you see here now Rohitash asking to your question, does time stop near black hole? So here it what happens, Rohitasha. If I take space as this, for example, if I take time as this, so you see if the time is very long, it is very long, then the time taken is more in the curved place rather than in the curved flat space. If I take just time as a simple coordinate, and if time slows down because of the extremely strong gravitational field, the curvature, just simply imagine that you're going in a straight line, instead that you're taking your turn around a pond and a hotel, etc., and it takes more time to reach you at your home. So this is a simple analogy. See the left hand side. A person is moving starting at 9 a.m. Okay. And you see the Schwarzschild radius on the left hand side. He reaches at 3 a.m. Why? Because it is a huge curvature that he has to travel. Okay. But here you see between Earth and that person, radius change for this is a question which Elvin has asked. Why Schwarzschild radius change with rotating mass? I will explain to you later. It is going to take some time. I'm so sorry. It actually changes when things actually rotates. Uh, in case of a spinning black hole, it has got a charge. So that charge actually creates a kind of an anomaly in terms of the radius. I will explain to you. Don't worry. Later come to me. I will just do it. So it is already 10 o'clock. So time slows down because it is just a coordinate, right? And here you see again, this is a video which I will send to you. This is why the gravitational redshift happens. So the person sees that it is taking a long time. The spaceship is never reaching the black hole, although the person has already crushed into the black hole, because the time is so long, it is taking so long that he will never see the person crushing inside the black hole, but it will go on and go on and go on, go on, because it will get a longer wavelength. So there is gravitational redshift, opposite is gravitational blue shift. So gravitational fields pulls the photon, and the loss of energy is the red. And this was actually a problem during that time in Göttingen and was solved by Emmy Noether. This was the research which was done by Reinhard Genzel, Andrea Ghez, and Roger Penrose. And you can see here, you see it closely. As the supermassive black hole, it is in the presence of the Milky Way. When the star S2 was quite far off, you see the star was white in color. Can you see this? It is whitish, star S2, which I have circled in
Yes.
yellow.
Yes,
Okay,
sir.
now it comes close, close, close. On the left hand side, you also see the star is white in color. Okay, now it comes close. The orbit becomes close. As it draws closer, you see that the redshift happens. And it was during that time, because until it comes very close to the black hole, measurement was not possible. And it happened in May 2018. And that actually proved not only gravitational lensing, lot of astronomical facts, as well as that supermassive black holes do exist. So that's it. I mean to say that was all about today's webinar. Now tell me, how was it? You have been silent. Tell me, did you enjoy? How was the overall idea about the webinar? How did you like it? I know it is very long, for long 2 hours, but that is how it happens, right?
Thank you very much.
So it was enjoying.
Okay. Now, last request
So
to
it
all
was
of
Yes,
you.
very
sir.
much
We really
interesting and
enjoyed.
informative.
Very well.
Okay.
Very much
Okay.
interesting and
Fine.
informative.
Okay. So
Yeah,
now
thank
here
you,
is the
sir. Yeah,
yeah.
this program was very enjoyable and very informative. Thank you so much
Okay.
for get us opportunity to join this program.
Great. Wonderful.
Thank you
Now,
so
Yes,
much.
one
sir. You
just
are
It
last.
will be
explaining each
great
and
if we'll continue
everything
the
of
lectures.
relativity
It
from
will be great if
scratch.
we'll continue.
I
It
will
was very
continue, definitely, definitely. So, who was Alessandro, you are joining from a very distant part of the world. What is your feedback? Can you tell me? Please don't leave. I have a small thing to do. Otherwise, I won't be able to give the certificate. Alessandro, what is your opinion? And Elvin, what is your opinion? Okay, so here is my last request to all of you. Please put up your feedback in this video. I have just shared with you with the links. Okay, and for the final, I wouldn't say final time, but can you all put on your camera? Let me see all of your smiling face. And please put on all your. Okay, hi. Okay, Vinay sir, how was it? Good.
And it
Ayushi,
was very
great.
informative. It was very informative. I
Great.
like your webinar.
Okay, so please put all your names in the chat box, complete name, so that I can issue the certificate by tomorrow. Please type out all your names. So, Ayushi, which class? I mean to say, are you in college or school? Because you're very young. You are on mute. I cannot hear you.
So I'm in first year college right now.
Okay, what
Just
subjects you're
working.
studying?
Physics, chemistry, and mathematics.
Physics, chemistry, and mathematics. Wonderful. Okay, great. So please put up your name, full name, right in here, because I'm going to issue obviously the certificates only to those who have been there till the last. It is not that I don't want to give it, but I see for 2 hours I have been. Don't take me wrong. I have been talking. I have been making these things only to make you understand that you really learn. Now, if somebody leaves in between, Vinay sir, you are one of
Yes,
the senior most. You
yes,
understand
yes.
what I'm trying to tell. That if
Me.
you leave,
Hello.
yes, sir, tell me.
Yeah, yes, sir. I'm very senior. I can say. My age is around 60, sir. And
60. Okay.
I'm working in BHEL as assistant general manager. And
Oh,
I
you
like
are
this.
the person who sent me that request. Okay. Okay.
I watch your videos in the YouTube, and
Okay.
I have purchased many books, sir. Student guide, like there are many books you have, that Maxwell equations and Schrodinger equation, then wave and all
Oh,
this thing.
okay.
But I have already arranged all those books, sir. I like, yeah, sir. So very
Okay,
nice, sir.
great.
Yeah,
Fine, fine.
yeah.
So I have already also shared my links. So Alessandro, good to see you. How are you? So did you enjoy the class? He is joining from
Yes, the
Beirut.
conference was very interesting, and enjoyed the whole webinar.
Great, wonderful. So I will just repeat with the names: Ashish Ranjan, Omar bin Abdul Aziz, M. Arif Akif Khan, Jubin Sebastian, Rohitasha Kundu, Ivan Kolchin Rivas, Ayushi Chaturvedi, Ashutosh Naik, Alessandro Paulo Hauman Limaska, Junaid Abbas Khan, Suhail Hafiz, Ahmed Rizwan. So anybody left? I think no. So I'm going to issue the certificate. Give me time. Sunday, tomorrow again. I have got the guests coming. By Monday, it will be there in your inbox, and I will also send you certain links so that you can later. Because you see, all these things will require a lot of time. And to see, we should divide it part by part so that one day in geodesic, etc. So in the live classes, I am actually doing all those things, going much more into the mathematical details. So thank you very much, everybody, for joining and enjoying this webinar. It was really wonderful. And
Thank you.
stay tuned. And
Thank you.
Alessandro, you're already there in my Instagram, so you can always contact me. I will be conducting this again in the month of December. But remember one thing, that every time I conduct the webinar, there is a change. That means it is not the same webinar which is being carried on. This month, I made a lot of changes in metric tensor. If you see my first webinar, it was something different. Second, I changed. So every time I am changing. I am thinking that next time I would put differential geometry a little bit more, so that that part is also taken care. So no webinar is just a same webinar that somebody has attended. They can do that, but it will carry on. So my request to all of you is that please put up a oh, you have bought this Quantum Mechanics by Griffith.
Yeah,
Is that the Griffith
yes.
book? Yeah. Okay.
That book.
Thank you very much. Thank you. See, Vinay sir at his age is now purchasing books on quantum mechanics. This is
Yes, sir.
incredible.
I used to read the many mathematics books, sir.
Okay. Okay. Great.
Yeah.
Great.
I'm having all of your
Prashant
suggestions.
Kumar,
Books are with me, sir.
okay,
Mm.
okay, great.
Party, party,
Mr.
sir,
Prashant,
party.
I hope you enjoyed this webinar also, Mr.
Yes,
Prashant.
absolutely enjoyable. Refreshing everything.
Refreshing. Sir, have you put on your name? Because your name is not there. Can you just type out your
No, I'll
name?
just because I'm actually first time in the meet. I just hello.
Oh, okay. Yeah.
If you can
So
write
you
it
can
down, my name.
fine, fine. You can later email or WhatsApp me your name. I will put it in the certificate.
Okay, okay, thank you.
Okay. Thank you very much,
Thank,
everybody, and see you
thank you.
soon, maybe in
Thank you very
December,
much.
etc. And I will start a new webinar in New Year, maybe on quantum physics also. My request to all of you is to put up a, I won't say I won't take your time, but put up a detailed, honest feedback at that link which I have sent to you, because that really helps. Because I'm a very small YouTuber, I am more of a teacher than a YouTuber. So people don't know me. So I want this to go and expand more and more, so that more people learn, more people feel happy, more people are enjoying mathematics and science. Thank you very much.
Thank you, sir. Thank you very much.